Let's do a few more review problems before we wrap up this unit of study. And so far, all the review problems you've seen are of simple harmonic oscillators, and here's just one more simple harmonic oscillator. The rest of the problems in this video lecture will be on either damped vibrations or forced vibrations. So here we have a 225 gram block attached to a spring whose K value is 90 newtons per meter. The amplitude of motion is 6 centimeters, and we have to figure out the frequency of oscillation, the maximum speed, the total mechanical energy, and we have to express position as some sort of function of time. So A, find F, that should be measured in hertz. B, find V maximum, that of course would be in meters per second. C, find the total mechanical energy. This is the same thing as the maximum kinetic energy, which in turn is the same thing as the maximum potential energy. That should be expressed in joules. And then D, what is position as a function of time? Well, we know it follows the form x equals a cosine omega t, so we're really just seeing, can you figure out what an expression is for omega? We certainly know what A is, 0.06 meters, because we're told the amplitude was 6 centimeters. If you want to draw a picture of this, easy to do. Block and spring, the mass is given as 0.225 kilogram, and the K value is given as 90 newtons per meter. So based off this picture, feel free to copy this into your notes if you're taking notes along with this video. Then also make note of these 4 questions. If you think you can work this out as we carry on with the rest of this problem, feel free. In the end, on the final slide, I'll provide the answers. So it's up to you to figure out what equations you can use to determine the answers for this case of simple harmonic motion. But I'm going to move on. Here's a problem I think we addressed in one of the earlier video lessons. For any mass spring oscillator, what's the position when the instantaneous speed is half of the maximum speed? We can state this mathematically. When is V equal to 1/2 of V max? Well, position as a function of time follows the equation V equals negative omega A sine omega t. What we need is an equation that expresses speed as a function of position. That's the equation that says V equals the square root of K over M times the square root of A squared minus X squared, which is the same thing as V equals omega times the square root of A squared minus X squared. Now you have maximum velocity when the object is at the equilibrium position. So V maximum is equal to omega times the square root of A squared minus 0, which means, V maximum is equal to omega A. So when is this quantity equal to 1/2 of V max? When is it equal to 1/2 of omega A? That's really what we're saying. So if omega times the square root of A squared minus X squared is equal to 1/2 of omega A, we could cancel out the omega and square both sides of the equation and get A squared minus X squared is equal to 1/4 A squared. This means X squared is equal to 3/4 of A squared. So we take the square root of both sides and find that X is equal to rad 3 over 2 times A, which is roughly 87% of the amplitude. So it might go against your intuition or best guess that it would be half of the maximum speed when it's halfway in between equilibrium and full amplitude. But then again, because the velocity is not constant and the acceleration is not uniform, it's probably not surprising that the answer isn't 50% of the way. Another key position we can ask about, this represents our block at equilibrium, and this represents our block at full amplitude. I guess that means at minimum amplitude it would be way over here with a very compressed spring. So there's the halfway mark in between equilibrium position and full amplitude, and we just found there's a special point right here equal to 87% the full amplitude. Now where's this other point? Maybe it's right here. So a question mark. If that represents the place where potential energy and kinetic energy are equal in value, then how can we express that in terms of the amplitude? So the only way that potential energy and kinetic energy can be equal is if the potential energy is equal to 1/2 of the total energy, but the total energy is the same thing as the maximum potential energy. In other words, when is 1/2 kx squared equal to 1/2 of 1/2 k a squared? So we can cancel out one of the 1/2s, we can cancel out the k's, take the square root of both sides of the equation, and we get x equals the square root of 1/2 times a, or better stated as x equals the square root of 2 over 2 times a, and that's the same thing as about 71% of the amplitude. What damping coefficient, what value of B would provide critical damping for the case of the mass spring system that was proposed in problem number 1? So I've recopied problem number 1. 0.225 kilograms connected to a spring with a stiffness of 90 newtons per meter. So if you were paying attention to the previous video lessons, you saw that critical damping, the coefficient, can be found by multiplying 2 times the square root of the product of mass and spring stiffness. So this is a very straightforward plug and chug problem. 2 times the square root of 0.225 times 90. And this gives us a B value of 9. Now wait a minute, what are the units? So the mass is in kilograms, and the stiffness was in newtons per meter. So we have the square root of Newton kilograms per meter. Now a Newton is a kilogram meter per second squared. So a kilogram meter per second squared times a kilogram divided by a meter. Meters cancel out, and we have the square root of kilogram squared over second squared, which is kilograms per second. So those are interesting units, right? The B value is 9 kilograms per second. Those are kind of misleading units in my opinion. It almost makes it sound like it's a measurement of the flow rate of material, but that's certainly not what drag coefficient represents. So I'm tempted to write it as 9 kilograms seconds to the -1, just to discourage that sort of thinking. Here's another problem that has to do with damped oscillations. A 2 kilogram block is attached to a spring with a stiffness of 200 newtons per meter. What's the natural frequency of this system? Well, the natural frequency is just the square root of k over m. That's the frequency it would oscillate with if there was no drag forces and you just pulled it back and disturbed it one time as a means of setting it into motion. So here we get the square root of 200 divided by 2, which is obviously 10 radians per second. Easy mental math on that one. Part B, if the damping coefficient is 10 kilograms per second and the system is mechanically driven by a machine that delivers a maximum force of 20 newtons, what's the resulting amplitude of vibration if the driving frequency is 5 radians per second? We just ramped this question up quite a bit. So let's write down some of these quantities. B is 10 kilograms per second. The driving force is equal to 20 newtons maximum. The amplitude of vibration is the question we have to solve for, and the driving frequency is given as 5 radians per second. Now here's an equation I don't expect you have committed to memory, but if you search your notes, you'll find that we've expressed a formula for a driven oscillator that says the amplitude is directly proportional to the maximum value of the driving force, and then it's inversely proportional to this long expression that has to do with the stiffness of the spring and the mass and the driving frequency and so on. So it's spring stiffness minus mass times driving frequency squared, all of that quantity squared, plus the drag coefficient squared times the driving frequency squared. So here we just have another plug and chug type of formula. 20 newtons divided by the square root of 200 minus 2 times 5 squared, all of that squared, plus 10 squared times 5 squared. Let's simplify a little bit. We get 20 divided by the square root of, let's see, 5 squared gives us 25, 2 times 25 gives us 50, and 200 minus 50 gives us 150. So 20 divided by 150 squared plus, 5 squared gives us 25, 10 squared gives us 100, so this is 2,500 or 2,500. So if we add 150 squared to 2,500, we get 25,000. So this is 20 divided by the square root of 25,000. And we get an amplitude of about 12.6 centimeters as the answer. It would be interesting for you to calculate what's the amplitude if it's driven at higher frequencies or lower. But those are the questions here in parts C and D. So here's the point of this one. We found that the natural frequency is 10 radians per second. Now, 5 radians per second would represent a case where the driving frequency then is less than the natural frequency. The amplitude response is 12.6 centimeters. If we were to drive the system at 15 radians per second, that's a case of the driving frequency exceeding the natural frequency. Now, the difference between the driving frequency and the natural frequency in our first case is a difference of, 10 radians per second compared to 5 radians per second. It's a difference of 5 radians per second. And the same thing is true for the next case. Instead of 5 radians per second below the natural frequency, part C is asking us what's the amplitude if it's driven at 5 radians per second above. So this ends up being an investigation on whether or not a graph of amplitude versus driving frequency is symmetrical about the resonant frequency. Let me express that graphically. We know that the greatest amplitude of motion comes when the driving frequency equals the natural frequency. That's the condition known as resonance. So if we imagine a knob that can control the driving frequency for a system, when it starts at 0 frequency, you don't have any amplitude at all because there's no driving of the system. Once you crank the driving frequency up higher and higher, the amplitude starts to become greater and greater and greater, and right at a driving frequency that matches the natural frequency, you get maximum amplitude. And then as you start to drive it at frequencies higher than the natural frequency, the graph comes back down. So if we draw an imaginary line passing through, is the curvature of the graph symmetrical about that point? The way I've drawn it, it doesn't appear to be, and let's see if our results from these calculations verify that. So when the driving frequency was less than the natural frequency, we got an amplitude equal to 12.6 centimeters. So now let's figure out when the driving frequency is greater than the natural frequency, what do we get? Let me clear a little room. So once again, amplitude is the maximum driving force divided by the square root of k minus mass times driving frequency squared, all of that quantity squared, plus drag coefficient squared times driving frequency squared. So we have 20 divided by the square root of 200 minus 2 times 15 squared, all of that quantity squared, plus 10 squared times 15 squared. Take this bit by bit. 15 squared is 225. 2 times 225 would be 450, and 200 minus 450 is negative 250. So we've got the square root of negative 250 squared plus, 15 squared is 225, 10 squared is 100, so plus 22500. And we get a value of 0.069 meters, or 6.9 centimeters. So the amplitude when driven 5 radians per second below the natural frequency, and the amplitude when driven at 5 radians per second above the natural frequency do not agree with one another, so it seems pretty clear that the graph is not symmetrical about the resonant frequency. Here's a pickup truck, and the pickup truck has a suspension system that includes some damping. Most of the shocks, in fact, I'm going to wager a guess that all the shocks in our vehicles are all spring shocks. Maybe it's a leaf spring, maybe it's a coil spring, but there's some sort of a spring mechanism incorporated along with a fluid resistance governed by a piston that introduces damping into the system. So if the mass of the car is 2,000 kilograms, and all these springs are in parallel with one another, when all the passengers, some people may be standing in the back of the pickup truck, and there's other passengers inside the vehicle, their total mass is all 500 kilograms, and that causes the truck to sit 4 centimeters lower than it would if the passengers weren't on board. So if we say F equals K effective times delta X, then the effective spring constant of all 4 of the shocks is equal to force divided by change in position. So this is a force of 500 kilograms multiplied by 9.8 newtons per kilogram divided by 0.04 meters. And that gives a K value of 122,500 newtons per meter, which sounds like a big number, and it is. And I would suppose that the springs that form the suspension system in our car are very, very stiff springs, and it would take an incredible amount of force to get them to compress a full meter. In fact, they never do compress a full meter, right? That would be 3.28 feet, unless you have a monster pickup truck that has an incredible value of freedom of motion. Then the likelihood of compressing your automobile suspension system of a full meter is not very likely. So if all of the springs are in parallel, we don't know. We weren't told how many. We were just told it's several springs. So if you were just to divide this effective spring stiffness by capital N, if capital N represents, not in this case newtons, but by capital N, I refer to the number of springs, then you would have the K value per spring. Part B, what would the natural frequency of vibration be for the fully loaded car if there was no damping at all? If we removed the pistons and just had the car on the springs, how would it like to vibrate when it's when all the passengers are on board? So frequency is equal to, I'm not sure if this question is asking for the frequency in radians per second or the frequency in hertz, so let's find both. So frequency in hertz is equal to the square root of k over m. So in this case, it's the square root of 122,500. Now what's the mass? It's not just the passengers and not just the car, it's all of it. So this would be 2,500. So this becomes the square root of 49, which gives us 7 radians per second. Well, frequency in hertz is the angular frequency divided by 2 pi. So 7 divided by 2 pi is equal to 1.11 hertz. Means it completes a little more than 1 vibration per second. Now, we weren't asked, but we might as well state it. Oh, no, we are asked. What is the period of oscillation? Period is the inverse of frequency. So the period is about 0.9 seconds. So it takes just a little less than 1 second for the truck to vibrate up and down. What drag coefficient would be required to make for critical damping for this car? So again, the formula for critical damping requires a drag coefficient equal to 2 times the square root of the product of mass and stiffness. So with the car fully loaded, the B value would have to be 2 times the square root of 2,500 multiplied by 122,500. Which gives a value of 35,000 kilograms seconds to the -1. Part D, assume the car suspension system is underdamped, so its B value is only 20,000 kilograms per second. And now everyone exits the vehicle, and now that they're out of the car, they all start pushing up and down on the bumpers. Some of you may have done this before on a vehicle, and they push up and down, and the car starts to vibrate and bounce up and down. They push with a force of 8,000 newtons, and their pushing is not continuous, right? If you've ever pushed up and down on a car like this, you're driving it at a certain frequency, so that if we graph the way you apply your force versus time, your force itself is sinusoidal. What's the greatest amplitude of vibration that they can develop for the truck? So this is the formula for maximum amplitude of a driven system. If we take the maximum value of force, so although your force is varying in time, we're told that its maximum value is 8,000 newtons. And that's the value that goes into this formula. Okay, so it's F max divided by the square root of, maybe you've memorized it by now, having gone through these example problems. What is it? K minus M times the driving frequency squared, all of that quantity squared, plus drag coefficient squared times driving frequency squared. So we're back to plug and chug. $8,000 divided by the square root of 122,500 minus, now that the passengers are out of the car, the mass is just out of the car, so it's 2,000, not 2,500. Driving frequency wasn't given here, right? So what's the maximum? Well, the most amplitude of vibration would be if the driving frequency is equal to the natural frequency. So when that happens, without even plugging in the numerical values here, keeping this part of the equation algebraic, If the driving frequency is actually the natural frequency, then that means it's the square root of k over m. But since we're going to square that frequency, then this becomes k minus m times k over m, and the m's cancel, so that k minus k gives us 0. So when driven at the resonant frequency, this whole part of our equation becomes 0, and then the rest of the equation is still b squared omega squared. So this is what was the value of b? Underdamped, 20,000. So b is 20,000, that squared, and then we have to multiply it times omega driven squared. So the greatest amplitude is actually infinite if they drive it at extremely low frequencies. No, I'm sorry, it's not infinite. It's the only way this term was 0 is if the driving frequency was the resonant frequency. So this term omega squared is the same thing as k over m. So our k value is 122,500, and the mass is 2,000. So we work this all out. 122,500 divided by 2,000. That comes out to 61.25. Then multiplied by 20,000 squared gives us a value of 2.45 times 10 to the 10th. We have to take the square root of that. And if we divide 8,000 by the square root of 2.45 times 10 to the 10th, we're dividing 8,000 by 156,525, which comes out to a value of about 0.051 meters or 5.1 centimeters. That's a lot of problem solving for one video lecture. Let's go back to the very first problem. Back to the easy stuff. Just good old simple harmonic motion. No B value to worry about, no driving frequency to worry about, just simple harmonic behavior. We're given a mass, you were given a spring stiffness, and you were given an amplitude, and you have to find frequency, maximum speed, total energy of the system, and describe position as a function of time. Hit pause on this video and work out your answers to parts A through D, and once you have it all worked out, then resume playing this video, starting now. Okay, welcome back. Now that you've worked out your answers, let me scroll down and reveal the correct answers to you. Hopefully you found that the frequency is 3.18 hertz, the maximum speed is 1.2 meters per second, the total energy of the system is 162 millijoules, and we can describe position as a function of time accordingly. Hey, thanks for tuning in.